It's a bit like taking a sledgehammer to a piece of rock.
You're listening to The Cosmic Cast. Hello, and welcome to another episode of The Cosmic Cast. I'm John Pernay-Fisher, and as per usual, right opposite me is Tom Harvey.
Hello.
And Marissa Lowe.
Hello.
And this week, all the way from downstairs, is Mark Nottingham.
Hello, good to be here.
Well, it's good to have you. So, you're new to the group, but also at the same time you've been here a long time.
I'm probably one of the oldest people here. I've been here for my undergrad. I did a master's year here and then my PhD.
And you've just started a brand new postdoc.
Yes, I have.
So, Mark, what are your main research areas that you're looking at then?
So at the moment, we're looking at the lunar regolith and the solar wind that's contained within that. So the regolith is the kind of very top layer of the surface of the moon. So all this finely powdered rock. There's this continuous stream of gas coming off the sun, and it implants itself onto the surface of the moon because there's no magnetic field and there's no atmosphere on the moon. And we're really interested in how this gas is distributed across kind of the various characteristics of the regolith. So it's got a lot of uses in situ resource utilization.
So that's, I guess, sort of if we're having manned missions to the moon again, or even rovers, making use of the material that's already on the moon for building things or fixing things for moon bases.
I guess the ultimate goal is to reduce the amount that you've got to actually take up into space, which makes all these missions a lot cheaper and easier to run, which ultimately, if we've got the same amount of money, it means we can get more missions for the same amount of money.
Yeah. So does the solar wind change the composition of the regolith then?
So when the solar wind impacts the moon's surface, it's moving at a high enough speed that it actually implants into the rock. And it does that by kind of a few hundreds of nanometers. But there are other processes on the surface of the moon that are constantly turning this layer of regolith over. So you've not always got the same rock on the surface as you started with.
Okay.
But I mean, really, I guess we've talked about noble gases a lot. A little bit, I guess, on this podcast. And this is really the main lunar application for noble gases, I guess. It's looking at solar wind and looking at cosmic rays.
So one of the easiest ways to look at the solar wind and how it's changed is to use noble gases. Kind of, as I'm sure you've mentioned before, they're diffusely spread across all solar system material. We use those gases as tracers for how this solar wind has been implanted, whether it's changed over time. Yeah.
So basically, it's a monitor of the sun's activity, I guess.
Yeah. So the project ultimately is trying to look at whether solar activity has changed between the start of the solar system and now. But to kind of first do that, we have to understand how these gases are partitioned into the regolith itself. And then we've got some further ideas for how to test the ancient solar wind compared to the modern day solar wind. So the moon kind of has existed alongside the Earth for almost its entire existence. So if we're really what the big science questions that we're interested in are how this radiation environment, including cosmic rays and solar radiation, has affected the Earth through these key developmental stages. So the first evidence that we see of multicellular life evolving on Earth. There are theories that there was an increase in the cosmic ray flux or the solar radiation that started causing an increase in the number of lightning strikes across the planet. And this ultimately kind of led that spark of energy that was needed to start these biological processes. So maybe not exactly multicellular life, but the first kind of chemical precursors that we'd look for.
Yeah, I mean, that's really cool. I guess it's like quite a sort of a fundamental thing to try and address, isn't it, really? Like, how has the sun changed over time? And I guess but it's so difficult to try and get that information out of the samples that we have, I suppose.
Yeah, it's really difficult to look at things because you're basically taking a sample from the surface of a satellite body. We're taking it from the surface of the moon, and we're looking at not only that kind of specific gas that we want to look at, but how that gas has been changed over the billions of years that this rock has existed for. So some of the rocks that I've been looking at previously are up to 3.2 billion years old. That's a very long time to have these records preserved without altering them at all.
So you've been looking at basalts, haven't you? Some of the Mare basalts.
Yeah, so we took some basalt grains from the Apollo 12 landing site samples. We were basically trying to look at whether you could take an individual soil sample. So when the astronauts were on the surface, they scooped a series of samples just from the very top soil. Obviously brought those back. And what we did was we went through one of those samples and picked out a series of, I think, 11 basalt grains that were about 2 millimeters across each.
Oh, okay. That's tiny.
Yeah. So a lot of this rock material is...
Right, yeah.
Some of it's microscopic.
Sorry, guys, I just assumed that you were subsampling like the main hand basalt units. I didn't realise it was from the soil. That's really cool.
So the idea of using these soil samples was all of those fragments of rock have come from somewhere else.
Yeah.
And there's this potential. One of our hypotheses was that you've built up this collection of rock fragments actually from a series of larger impacts across the surface of the moon.
Yeah.
There's an idea that a lot of the material covering the Apollo 12 landing site has actually come from this crater called Copernicus, which is hundreds of kilometers away.
Yeah.
But alongside that, you've got all these other craters adding material to the area.
So that's a real mixed bag of stuff. I hadn't actually realised that it was sampling stuff from Copernicus. That's quite cool.
People haven't really looked at this before, to my knowledge at least, of using an individual soil sample to try and pick out these key geological events that we look for to kind of organise the ages of things, kind of when things happened on the surface of the moon. So the main way that we've been looking at these things is by working out their cosmic ray exposure age. And basically when you take a fragment of rock and you expose it to a radiation flux, so it's sat on the surface of the moon, it's continually getting bombarded by these high energy radiation particles.
Just background to the galaxy. Do we know where they come from, actually? Or just
the cosmic
rays?
ray background?
Yeah, there are two kinds of cosmic rays, really, in the broadest definition of what a cosmic ray is. Some of them come from the sun, and we call those solar cosmic rays.
Yes, yeah.
They have a much higher production rate. Kind of they produce more cosmogenic gas within a sample than the galactic cosmic rays, but they're a lot lower energy than galactic cosmic rays. And galactic cosmic rays we don't really know where they come from. We suspect that they're from supernova explosions.
Right. That's cool.
Yeah, but generally we see that the cosmic ray flux is both isotropic, so it means regardless of what direction you're looking, you're getting the same rate of flux.
But in essence, these are really high energy particles, and so when they interact with material on the lunar surface, they cause these chemical reactions that cause target elements in the minerals to turn into noble gases.
Yeah, so there are specific elements within these fragments of rock that when one of these high energy particles hits it, it's a bit like taking a sledgehammer to a piece of rock. The energy is enough to actually completely break apart that atom, and it generally, as part of that, will form a noble gas atom as well as another daughter product. Because this happens at a particular rate, and a rate that we can measure it through nuclear equations and kind of our understanding of physics, we know how much of this gas should be produced over a particular amount of time.
Yeah.
And from that, it's then a simple process of, you measure how much gas is within the sample, providing you can isolate that cosmogenic gas from anything else that's in there, and work out how many millions of years it would have taken for the gas that you've measured to accumulate based on those kind of theoretical equations that you're using.
Yeah, I mean, that's really cool. And it's basically how It's the backbone, really, of how old we know a lot of things are on the surface of the moon, aren't they, I suppose?
Is this also how we know how old things are that land on Earth as well?
Yeah, it's a similar principle. It's a slightly different set of isotopes. I think, is it beryllium-10 people use on Earth? Yeah, but it's a similar principle, because obviously the cosmic ray flux is shielded because we've got an atmosphere somewhat, whereas stood on the moon, you're getting the full blast of cosmic rays to the face.
Mm-hmm. So what noble gases do you look at in particular?
So within the work that I'm doing at the moment, we're looking at the light noble gases.
So that's helium, neon, argon.
Yeah. In my other work, I've used krypton as well. So interestingly, krypton can be used for kind of surface exposure for meteorites, because the krypton chronometer is built up using a radioisotope. So krypton-81 decays over time.
But krypton-81 is quite interesting because it's there's no other process that produces it. Is that right?
Yeah, so krypton-81 is purely cosmogenic.
Yeah, so whereas some isotopes are shared between other processes, that's why krypton-81 is used so much, isn't it?
Yeah, and so as you expose a piece of rock to this radiation, you build up the amount of krypton-81 within the sample, and that scales linearly as it's exposed. But on top of that, you've also got nuclear decay going on, and that's a random process. And effectively, because it's random, the more atoms of krypton-81 you have, the more likely you are for some of it to decay over that period of time. And what ends up happening is after kind of 1 or 2 million years, you end up with the concentration within the sample of krypton-81 being level. And that, where it levels out, is based on the chemistry of the sample. So whereas for neon, argon, helium, you have to have a fairly good idea of what the chemistry of your sample is, with krypton, you don't, because it, within the system itself, self-corrects.
Yeah. Am I right in thinking it's the most robust cosmic ray chronometer that we have, or one of them anyway?
I mean, certainly because my PhD was based on it, I would say that.
So is this work sort of a direct follow-on from the stuff that you did during your PhD, or is it adjacent?
It's definitely adjacent. So I actually started this project on the back of a Leverhulme Trust grant that was awarded to someone else.
Because you did your PhD on CAIs, didn't you? I think.
Yeah, so these little fine-grained...
Calcium, aluminium inclusions?
Yes.
How have you found transitioning from chondrites and CAIs to lunar stuff?
It was challenging at first. I mean, a lot of the principles are the same.
Yeah.
I think the most difficult and challenging part of it was wrapping my head around this dependence of the systems I'm using now on chemistry. There's a lot of processes and the instruments that we use to look at these things work differently to the one that I was used to as well. So changing the way you're looking at the problem and how you're handling data, it was tough to get my head around, but I think I'm just about there now.
So we were just saying that you were looking at CAIs during your PhD. What sorts of things were you looking at more broadly? Like, what was the aim of your PhD work?
So my PhD really got divided into 2 sections. Part of it was developing the instrument that we used to look at these samples, which was the resonance ionization mass spectrometer for krypton isotopes, or Rimsky, because that is really quite a mouthful to say every time you're speaking. The other part of it was, it was based on this idea that CAIs, because they're some of the earliest things to form in the solar system, and because we've got this group of CAIs called the fun CAIs.
Oh,
I can't remember what that stands for. But these unique CAIs don't fit chemistry-wise with the rest of the collection.
Okay.
So there was this quite far-flung idea that maybe they came from extrasolar sources.
Okay.
So they were originally the remnants of a supernova explosion that had been flung out into space and had arrived in the solar system prior to it all being compacted. I'm not sure how much I believe that idea. It's
because what's the sort of more traditional view on where CAI material comes from?
Oh, that's a whole can of worms to open.
That's
there are
just
lots
sort
of
of true for all
ideas.
primitive components.
There are
aren't
lots of competing ideas about where CAIs came from. We know they're some of the first things to crystallize in the solar system, and we know that they're the highest temperature minerals that we see.
Okay.
But I think the last time I checked, there were 5 or 6 competing models that could explain some of the evidence that we see through CAIs, but not all of them.
Okay.
So how did you get into planetary science? You said you did your undergraduate here. Did you do the planetary science course from the start, or?
No, so I started on the geochemistry pathway that we offer in Manchester.
Mm-hmm.
It was a bit of a roundabout way that I actually got to doing that in itself. So before starting my undergrad, I went to one of these university open days and basically by complete fluke chance met an admissions tutor who was also the senior academic for their earth sciences department.
Mm-hmm.
And at that point I had quite an interest in chemistry, physics and geography. The school that I went to didn't actually offer geology as an option, and to the point I didn't know it existed as a subject. I thought it was just rolled into geography in some way.
Mm-hmm.
And by complete fluke chance of meeting this person, they introduced me to the idea of doing earth sciences, and through that ended up at Manchester, went for the chemistry option, and by kind of the units and courses that you do through that, rekindled. I've always had a bit of a love for planetary science, and I've definitely been a space geek from an early age. But it's kind of through the people that I met and had as lecturers that they got me interested in the idea of doing research, but specifically planetary science research. And that was actually by, again, a fluke chance when I was looking at options for my master's year, which was built into my undergrad. One of the research projects that was on offer was one with Professor Jamie Gilmore here in Manchester, using this novel mass spectrometer. And I went, great, it's something that's, there's a bit of mechanics, there's, it's quite hands-on lab work, but it's also got planetary sciences in there as well.
Yeah, it's a good combo.
So I leapt on that opportunity, and through the course of that year, decided I wanted to go further and pursue a PhD with it.
I think it's quite common that people don't do geology and don't know about geology as a kind of gateway to lots of other different sciences. Because I didn't do geology at school either. I also did maths, physics, chemistry.
Yeah, very few schools, in fact, offer that.
Yeah, and I actually think it's a fantastic university subject because it's so interdisciplinary.
Yeah,
because it's
it's
geography,
the application of science, isn't it? Really?
Yeah, geography, biology, chemistry, physics, whatever you want. And as you say, as you go, you can actually change your interests and decide that you want to follow a different pathway. So, I've basically done exactly the same thing because I did entirely chemistry and igneous terrestrial stuff for most of my undergraduate, and now
look at you now,
meteorite rocks. But it's pretty neat.
So was your master's project related to the PhD project you ended up doing?
So the master's project that I did was using Rimsky, or the resonance ionization mass spectrometer for krypton isotopes.
Thank you, Mark.
We were using that to look at a meteorite called Puerto Lápiz, which is part of the HED suite. This is a meteorite that's from an entirely rocky body. We think from the asteroid 4 Vesta. And really, the ultimate aim was to just work out how long it had been flying around the solar system between being kicked off the asteroid and arriving on Earth. Along with part of that, what we started doing was taking a series of measurements that had been made by other people for the exposure ages of meteorites, specifically to the HED suite, and we tried to model how many impacts would be needed on the asteroid to release the number of samples with the ages that were measured through computer modeling. So yeah, the end result, we did come to an answer. This is a long time ago now, but there was maybe 6 impacts that explained all of the samples that we were looking at.
That's cool. That sounds like a really good master's project, especially because it did set you up with using Rimsky for your PhD. So you said for the PhD you were looking at like developing Rimsky as an instrument. What does that entail?
So Rimsky is a phenomenally complex instrument. It uses a series of lasers to take krypton atoms and boot an electron from each of them. The way it works, so this is an ultra-sensitive mass spectrometer. I would kind of brag that if we can't see krypton in a sample, nowhere else can. There are one or two other instruments that work like Rimsky, but
that's a pretty good advert. I think you should stick that on the side of the instrument.
If we can't measure your krypton, no one can.
I tried to persuade Jamie to put that on the instrument, but he was having none of it. So the way it works, by using laser light to ionize the gas, is if you were to take an atom and look at the electrons on the outer surface of that atom, each of those has a specific energy attached to it. And there are certain energies that electron is happy sitting in. It will sit there for longer than in between those energy gaps. And each of those gaps also corresponds to a wavelength of laser light. So what we can do is we can target a specific electron and say, we're going to put one wavelength in initially to get it to jump one transition. And if you do that enough times, you eventually get to the point where you need a very small amount of energy to kick the electron out of the atom. And that's the way it ionizes the gas, which then allows us to kind of spread the isotopes out from each other according to their mass and ultimately detect and measure what's in the sample. I have no idea if that's a way of explaining photoionization.
Yeah, so how did you have to develop it, though?
So the way we were developing it, to actually form those laser wavelengths, one of the first transition within krypton that we were using lies in the vacuum ultraviolet range. We're trying to form this very specific wavelength of light, but you can't buy a laser that produces this. So you've got to come up with a way of making it yourself. And what we did was the instrument already had a gas cell on it, and it was a mix of xenon and argon to very specific ratio with each other. As the beams that ultimately formed that wavelength passed through this cell, they would interact within a xenon atom, again, kind of build themselves up through this resonance step, but not get to the point where it would kick the electron out of the atom, and it would decay back down and ultimately release this wavelength that we wanted. When I took over the instrument, the way that we worked out the gas mix was effectively to quickly open one gas bottle and quickly shut it, and then quickly open another and quickly shut it. As you might imagine, that's not the most accurate way of doing this, and it would take weeks, if not months, to set this instrument up just for one run. So basically, I didn't want to sit around spending months filling and emptying a gas cell. So instead, I stuck on two little controllers, which allowed a variable rate of gas into that cell. Basically allowed me to play around with the ratio that was actually in the cell and see where the peak production for this wavelength was, and how best to run the instrument. I think all in all, over everything that I did, I doubled the sensitivity of the instrument to how it was when I took it over.
Nice one.
So you and Nat Curran, who we've had on before, recently had a paper out only this month, actually. It's been properly released, I think.
Yeah, it was part of the special edition of the Planetary Space Sciences Journal, specifically looking at Prospect, which is an instrument package on a mission to the moon. I was personally quite excited because it's the first publication that I've got out since starting, I guess, my career in planetary sciences.
Yeah, it's always good and always exciting.
So yeah, the paper was effectively a database of noble gas measurements and calculations that have been run on those through as many literature sources as we could find. I mean, I can't claim too much credit for this. It was definitely, it was Nat's project. It was based from her PhD and the work she's done since. I just inherited and basically was asked to go through that database a lot.
But basically, it's the most comprehensive noble gas database for lunar materials out there.
Yeah. I'd like to say we found pretty much everything out there. I mean, no doubt there are things we've missed, but that's part of the science and part of building a database like this.
Yeah, I mean, they're useful tools. Like, it's really handy having these kind of like big databases for people to go back and check numbers and all that kind of stuff. So I'm sure it'll get highly cited.
What format does that take? So do you, when you write that as a paper, is it the kind of the description of the way that you found all of that information, and then there's like a spreadsheet as a kind of additional supplement, or?
So the paper really focuses on a meta-analysis of all these measurements that have been taken, as well as looking at maybe the gaps within the current record that we've got. Out of the samples that were brought back from the moon, there are quite a few that have never been measured. That's for a variety of reasons, but there are these gaps within our sample knowledge that maybe an additional bit of information about how the moon evolved is sat within one of those samples.
So you're sort of doing a literature review at the same time as compiling all the data?
Yeah, I'm hesitant to call it a literature review because normally for a journal you've got to be invited to submit a review article, and that was something we were really keen to stick away from. Both of us are kind of still starting out in our careers, and normally you're only asked to do that years down the line. Yeah, ultimately we wanted to create a resource for people to use and kind of build a paper around understanding that resource.
Yeah. Well, we'll put a link to that in the description, so if any of the listeners fancy thumbing through some noble gas data for the moon, you can do so.
So something that we ask everybody that comes on the Cosmic Cast is, if you weren't doing what you're doing now, either inside science or outside science, what do you think you'd like to be doing?
I can't believe I didn't think of an answer before coming here, because I know you always ask this question. I've always thought I'd like to do something cooking related. One of the biggest hobbies that I've got outside of doing science research is cooking. I go on weekends away hiking with people, and for a group of 16, 20 people, we'll do pretty much all the cooking while we're there.
Wow, you're basically a chef at that point, really. Those
well,
sorts of numbers.
It is interesting.
Chef implies I get paid.
People say cooking.
Yeah, I know. So me, Elliot, Mark, I think we should start our own restaurant, pack in the academia and
I'm sure I can
go
find
start
some
a
room in
restaurant.
the Williamson somewhere.
Yeah.
Would you have all your dishes named after isotopes?
No.
No, okay.
Absolutely not.
I would chase people around the kitchen with a cleaver.
Yeah, a lot of people say cooking. So for me, it's sort of it's a nice, like, relaxing thing to do. But then also, like, with baking, it's a bit of chemistry as well. So I like to think that makes that side of my brain sort of a bit happy to do a bit of baking and cooking.
And then you get to eat it afterwards.
Yeah, exactly.
This is the bit I enjoy.
It's like there's always a reward. So
It's definitely that kind of creative science side of it that's interested me. I guess the creative side goes hand in hand with doing research like planetary sciences anyway.
yeah.
Quite often we're coming up with these ideas to answer hypotheses that are, they do require these off-the-wall ideas.
Thinking outside the isotope plot.
That was a good one.
How long have you been thinking of that for? That's horrible.
I don't have a response to that.
No, there's no response. There's no response.
Well, thanks very much for coming on and talking to us today, Mark. And I'm sure we can have you on again in future when you're a bit further along in your postdoc work. But anyway, have a good week, everyone, and see you next time.
Bye.
Thank you for having me.